In this video, we will briefly overview orthogonal bases. First, for background, we'll look at what the definition of orthogonal vectors are, and then we'll talk about orthogonal vectors being linearly independent, and then we'll talk about orthogonal bases. We'll also talk about why orthogonal bases are useful, and that is because determining the coordinates, the scalar multiples of expressing a vector in terms of the linear combination of a basis. If the basis is orthogonal, there's a very easy way of determining the coordinates. And last, we will not cover this, not because it is not important, but because it's a very mechanical kind of formula-driven thing, so I'm not going to spend time discussing it, but to say if you have any given basis that's not orthogonal, you can construct an orthogonal basis from that using the Gram-Schmidt method, but we will not cover the Gram-Schmidt method. First, some background. The idea of orthogonality is a generalization of the geometric concept of perpendicular. So in R2 and R3, we say a vector u and v are perpendicular if u transpose v equals 0. If you know, if you've gone through vector calculus, u transpose v is equivalent to the dot product between u and v. So for example, if I have the vector u is equal to 1, negative 2, which I've drawn here, and the vector v, which is 6, 3, which I've drawn over here, then u transpose v, here's u transpose times v, so I get 6 minus 2 times 3 is minus 6, so I get 0. So this is how in vector calculus we prove that vectors were perpendiculars. We took the dot product and we saw that their dot product was 0. And we're going to extend this idea and say orthogonal vectors, if we have a set of vectors u1, u2 up to up, and it's a set of orthogonal vectors in Rn, the set is said to be an orthogonal set if ui transpose u is equal to 0 when I does not equal to j. So when these two vectors are not the same vector, then their dot product is equal to 0. So our next example is with vector u1 is equal to 1, 0, 1, 2, u2 is equal to the vector 1, 1, negative 1, 0, and u3 is equal to the vector 1, negative 2, negative 1, 0. So if I do u1 transpose times u2, so here I have u1 transpose times u2, then I have 1 times 1, 0 times 1, 1 times negative 1, and then 2 times 0, which is just 0. So when I sum these together, I get 0. Similarly, I can verify that u1 transpose u3 and u2 transpose u3 is equal to 0. Since, taking these vectors, taking them two at a time, looking at the transpose of one times the other vector, we keep getting 0. Since they're all equal to 0, we say that S is an orthogonal set of vectors in R4 because it's a four-dimensional vector. We have the following theorem that orthogonal vectors are necessarily linearly independent. So if S is a set of P non-zero vectors in Rn, if S is orthogonal, if it's an orthogonal set of vectors, then S is a linearly independent set of vectors. Next, we have this comment, any orthogonal set containing P non-zero vectors from a P-dimensional subspace W will be a basis for W. And we're using these properties of a P-dimensional subspace, which we discussed in our last video about dimension. We said if we had a subspace W that has dimension P, then any P linearly independent vectors is a basis for W, or any P vectors that span W is also a basis. So once you know the dimension of W is P, so you need P vectors to be a basis. And if you have P linearly independent vectors, then it's a basis. Or if you have P vectors that span W, then it's a basis. So that's what we're using here. So if the dimension of W is P, then P linearly independent vectors is a basis for W. And here we say we have P orthogonal vectors, but our theorem says those orthogonal vectors are linearly independent, and therefore they will be a basis. Finally, we have the definition of an orthogonal basis. Let W be a subspace of Rn and B be a set U1, U2 up to UP, a basis for W. If B is an orthogonal set of vectors, so not only is B a basis, but it's also orthogonal, then B is called an orthogonal basis for W. Furthermore, if the length of each of these basis vectors is equal to 1, then B is said to be an orthonormal. Both it's orthogonal and it's also normal. In other words, normal being length 1. It's an orthonormal basis. Our example is verify B is equal to 1, 2, 1, and the vector 3, negative 1, 1, and the last vector 1, negative 4, 7 is an orthogonal basis for R3. We are going to start by verifying that B is an orthogonal set. So we take V1 transpose times V2. So B1 times V1 dotted with V2. So that's 1 times 3 plus 2 times negative 1 plus 1 times negative 1, and that's equal to 0. Similarly, we take V1 transpose times V3 and V2 transpose times V3. And we get they are all equal to 0, so we have verified that B is an orthogonal set. By our theorem, then, we have an orthogonal set, so we also have a set of linearly independent vectors. So these vectors in B are linearly independent, and again, by that properties of a p-dimensional space, so if the dimension of W is equal to P, then any set of P linearly independent vectors in W is a basis for W. Since R3, where were we? We're trying to verify it's a basis for R3, so the dimension of R3 is 3. Since we have 3 linearly independent vectors here, then it must be a basis for R3. So we have a corollary. Let W be a subspace of Rn where the dimension of W is equal to P. If S is an orthogonal set of P non-zero vectors, and is also a subset of W, then S is an orthogonal basis for W. So the next topic we have is, well, why are orthogonal bases important? And that is because it's really easy to find coordinates in an orthogonal basis. And what do I mean by coordinates? Remember when we have a basis, so let's just say we have a basis B is equal to W1, W2, W3, then we know any vector V can be written as a linear combination of W1, W2, W3, since they are a basis. These coefficients, A1, A2, A3, the scalar multiples that go in front of your basis vectors, those are also referred to as coordinates for reasons that we'll talk about in a future chapter. So remember, previously when we wanted to find these coefficients, we set up the augmented matrix, right, with all the coefficients. We row reduced it, then we back solved, and we figured out what these coefficients were. However, if our basis is orthogonal, we have this simple method of finding these coordinates. And the way we do that is if we want to find A1, for example, because A1 is associated with W1, our first basis vector, we multiply both sides of this equation by W1. So here I have W1 times V, and then W1 times the linear combination that equals V. And if we kind of rearrange some of the terms on this second side, the right-hand side of the equation, we have A1 here and the W1 transpose times W1, the W1 transpose times W2, and the W1 transpose times W3. Well, this part, W1 transpose W2 and W1 transpose W3, those are going to be equal to 0 because W1, W2, and W3 are orthogonal. So whenever these are different, this is 1 and 2 and this is 1 and 3, you're always going to get 0. So these disappear. So what you're left with is this A1 W1 transpose W1 is equal to, and then the left-hand side of this equation was W1 transpose V. So we'll do an example. So now if we want to express our vector V equals 12, negative 3, 6 in terms of the orthogonal basis 1, 2, 1, 3, negative 1, negative 1, 1, 4, 7. And again, just I want to remind you, if this were not an orthogonal basis, you would set up this vector equation, right, where A1, A2, and A3 are the scalar multiples that would give you your linear combination. So you would set up this vector equation, you would solve the augmented matrix, and then you do back solving in order to get A1, A2, and A3. But because we've been told this is an orthogonal basis, we can do this in easier way. So again, we want to express the 12, negative 3, 6 as a linear combination of the 1, 2, 1, 3, negative 1, and 1, 4, 7. So to find A1, because it's associated with the 1, 2, 1 vector, I'm going to multiply both the left and the right-hand side of this equation by 1, 2, 1. So here I have 1, 2, 1 transpose times the 12, negative 3, 6 equals, and then I have A1 times my 1, 2, 1 transpose times 1, 2, 1. My A2 times 1, 2, 1 transpose times my 3, negative 1, 1. And then A3 times 1, 2, 1 transpose times my 4, negative 1, 4. And then again, if I look at this, well, actually, I'll just do the calculation. So 1 times 12, and then 2 times minus 3 is minus 6, and then 1 times 6 is here, and then equals to A1. Then I multiply this out. I have the 1, the 4, and the 1. But now look what happens to A2. This is going to be 3 minus 2 minus 1. So this is going to 0. Then I have my 1 minus 8 and 7. This goes to 0 as well. And so what I have is here I have 12 equals 6 times A1. So A1 is equal to 12 divided by 6 is equal to 2. Similarly, to get my A2, since A2 is associated with the vector 3 minus 1 minus 1, I'm going to multiply both sides of the equation by 3 minus 1 minus 1 transpose. So here I have 3 minus 1 transpose times my 12 minus 3, 6 equals A1 times my 3 minus 1 transpose my 1, 2, 1 plus A2 times my 3 minus 1 plus 1 transpose times my 3 minus 1 minus 1. Are these two minus 1s? I don't remember. Yes, it is. And then A3 times my 3 minus 1 times my 1 minus 4 minus positive 7. Sorry, I'm not able to read anymore. So anyway, I do my multiplication here. I get 3 times 12 is 36. My minus 1 times minus 3 is positive 3. Minus 1 times 6 is minus 6 is equal to A1. And now look here, I have 3 minus 2 and minus. This goes to 0. And then I have A2, my 9, negative 1 times negative 1 is positive 1. And negative 1 times 1 is positive 1. Plus my A3, and here again I have 3, positive 4, negative 7. This goes to 0 as well. So what I get is A2 is equal to 3. Similarly, I can find A3 is equal to 1. So as you can see, it's super convenient if you have an orthogonal basis to determine these coordinates, much nicer than what we were doing before. But of course, you can't just sit around hoping to get an orthogonal basis. So we have this method called Gram-Schmidt. So if you find a basis, which we have had practice finding basis for things, but if you have a basis, Gram-Schmidt gives you a way of constructing an orthogonal basis. But as I had mentioned in this video, we will not be covering Gram-Schmidt except to say that it is a process for constructing an orthogonal basis from any given basis. So that's it for this video, a quick review of orthogonal basis. First, we talked about what it meant to be orthogonal. That is that U transpose times V equals 0, means U and V are orthogonal. And then we said that if we had a set where we take 2 at a time and they were all orthogonal, then our set was considered an orthogonal set. And then we had this theorem that said orthogonal vectors are linearly independent. So that was an important theorem. We also talked about the definition of orthogonal basis. Essentially, it was if you have a basis that also happens to be orthogonal, then an orthogonal set of vectors, then it's also an orthogonal basis. And then last, we talked about the importance of orthogonal bases is that determining these coordinates when you want to represent some vector as a linear combination of your bases, it's very easy to find the coefficients that multiply each of the basis vectors if your basis is orthogonal. And then last, well, you don't want to sit around waiting for some orthogonal basis to come up. If you're given a basis, you can use the Gram-Schmidt method to construct an orthogonal basis. So that's it for this video. Thank you for watching.